a point with a negative first coordinate and a positive second coordinate, basically a negative x coordinate, and a positive y coordinate lies in which quadrant? We're supposed to be able to tell this. A negative first coordinate, with the x coordinate is negative, it means it's going to be to the left of the y-axis, and if the y coordinate is positive, it means it's going to be above the x-axis. So evidently it's over here somewhere. It's in quadrant 2. So quadrant 2 for that one. Second quadrant. Quadrants. In which quadrant would we find negative 2, 6? Is it right there? Looks good. Negative 5, 0 is not on, well, it's not in a quadrant, it's on an axis. Whereas negative, what? Quadrant 2, sorry. There we go. Negative 5, 0 is where? Right there. X-axis or y-axis? That was the question I was trying to ask. X-axis. If the y-coordinate is 0, it's on the x-axis. If the x-coordinate is 0, it's on the y-axis. And 2, negative 3. X is positive, y is negative. So right there. And which quadrant will we find 2, negative 3? That's quadrant 4. I don't know why it feels compelled to scramble quadrant 3, quadrant 1, quadrant 4, quadrant 2. Make them hard to find, I guess. Best score, definitely. A distance formula. On the test, this particular one, there are various different formulas that you want to memorize. When we get to the section on straight lines, you run into several formulas: slope and point slope, slope-intercept form. In this section, we look at one that shows up in this section, not too many others. It'll show up here, and also when we look at circles, the distance formula. So you want to make sure that you have the distance formula D equals the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. Basically, it does what you would do if you were drawing the picture and calculating the side lengths of a right triangle and using the Pythagorean theorem. It kind of does that for you without having to draw the picture and do everything that goes along with that. All we have to do is decide that x sub 1 equals negative 1, y sub 1 equals 3, x sub 2 equals 0, and y sub 2 equals 1, and substitute into the distance formula, and the calculations, well, they're not done for us, but in so much as the formula gives us the setup, it will take care of it for us. So the difference in the x's basically will be the horizontal distance between the 2 points. X sub 2 minus x sub 1, 0 minus negative 1. There we go. The absolute value of that would be the horizontal distance, but we're squaring it, so it's actually not necessary to take the absolute value. Y sub 2 minus y sub 1 would be 1 minus 3. So D equals the square root of, what is 0 minus negative 1? 1. So 1 squared plus negative 2 squared. D equals the square root of 1 plus 4. So it looks like the square root of 5. No need to punch this one up on a calculator. It's just wanting the square root of 5. So let's see if I can give it that. Radical 5. Good. The midpoint formula also should be on your list of important formulas to be memorized. Basically, we want the point whose x-coordinate is halfway between the two x-coordinates and whose y-coordinate is halfway in between the two y-coordinates. So we average the x-coordinates. We average the y-coordinates. The midpoint formula, x sub 1 plus x sub 2 over 2. If we want to find the average of a bunch of numbers, we add them all up and divide by however many there are. If we want the average of just 2, we add them together and divide by 2. So the average of the x-coordinates, the average of the y-coordinates. So with the same x sub 1, y sub 1, x sub 2, y sub 2, it's going to be negative 1 plus 0 over 2 for the x-coordinate, and 3 plus 1 over 2 for the y-coordinate. So we're wondering what's halfway in between negative 1 and 0. That's negative 1/2 or negative 0.5. It'll probably accept. What's halfway in between 3 and 1? 4 over 2, which is 2. So there is the midpoint. Halfway in between the 2 points, negative 1/2, comma 2. I'm thinking it would probably accept negative 0.5 for the x-coordinate there. Four, 5, and 6, I think, are additional applications involving the distance formula, possibly also the midpoint formula. That's a little bit more of the same, so I'm going to skip that one. 5, it looks kind of awful because of the decimals. I don't think it's that much worse, though, because when you subtract, I think the differences are reasonably nice. Blow that up a little bit. The numbers are just way too small. Sorry about that. A little bit easier to see here, I hope. Label these x sub 1, y sub 1, x sub 2, y sub 2, and then apply the distance formula. So neither x sub 1 nor x sub 2 is an integer, but their difference is. It's going to be 7.5 minus 2.5, and then we'll square that. Also, the difference between the y-coordinates is an integer. 7.4 minus 3.4. Take the difference and square that. So 7.5 minus 2.5 is 5. 7.4 minus 3.4 equals 4, or 4.0. So we get 20, the square root of whatever 25 plus 16 is. So that's the square root of 41. Square root of 41 there. The midpoint, I think the 2.5 and the 7.5 will not be terribly troublesome, but maybe the 3.4 and the 7.4, if you want to punch a couple buttons on the calculator. Add the x's together and divide by 2. Add the y's together and divide by 2. So 10 divided by 2. For the x, I believe the number 5 is halfway between 2.5 and 7.5, so that would make sense. For the y's, 10.8, that's not terrible, I guess, over 2. It would have been terrible if I left out the 2. 10.8 divided by 2 equals 5.4. There we go. So it looks like 5.4 is the midpoint here. Sure, and include the parentheses. And 6, I would think maybe more of the same. Yeah, more of the same with one of the coordinates negative, so I think we can move on to section 2.2. .2, the two main sections involve symmetry and circles. 2.2 part 1, I think, is symmetry. And also sketching graphs by finding intercepts. Let me just flip through this one real quickly and make sure. Graphing, okay. Three main parts then. Symmetry, a little bit more symmetry. Okay, so a little bit of graphing, a little bit of symmetry in this first part. Second part, I think, does have the instructor created symmetry problems where we have to substitute negative x for x, negative y for y. We'll do a little bit in this, about a little bit of that in this section. Without sketching the graphs, the graph, find the x and y intercepts. Okay. I would think having the x and y intercepts would go a long way toward helping us sketch the graph. I don't think I would want to sketch the graph without first finding them, unless I had a calculator sketch it for me. Key procedure here, if we want to find an x-intercept, we observe that points on the x-axis all have different x-coordinates, but they all have the same, what? Y-coordinate. What's the y-coordinate of every point on the x-axis? 0. So to find an x-intercept, we substitute 0 for y and solve it for x. So for the x-intercept, let y equals 0, 6x plus 5 times 0 equals 120, and solve the resulting equation for x. 6x plus 0 equals 120. 6x equals 120, and we divide both sides by 6. X equals 20. So it's going to want, is it going to want a number, or is it going to want an ordered pair? It doesn't say ordered pair. I'm thinking maybe if we just say 20, it'll be okay with it. So I'm going to try and see if it likes it. The x-intercept, simply the number 20. It's okay with it. It might not have been okay with the point 20, 0. I like to think of intercepts in general as points where the graph crosses an axis, x-axis or y-axis. But when it's specific and it says x-intercept, then, and I just say 20, then that answers the question, because you know the y-coordinate has to be 0. What's the y-intercept? Well, follow the same procedure, except that let x be 0. Every point on the x-axis is equal to 0, so we want the point that has an x-coordinate of 0 to solve this. So to find the y-intercept, let x be 0. 6 times 0 plus 5y equals 120, and solve it. 5y equals 120, so y equals whatever 120 divided by 5 is. Maybe 24. So whereas I'm thinking, I probably shouldn't even write it. In case somebody looks at this someday, 20, 0 or 0, 24, those are the points that I would plot. But really, MyMathLab wants 24. There. A little different when it's quadratic. I think I have an example in the notes where I find x and y intercepts of the circle, and the circle is going to be quadratic in both the variables x and y. This one is linear in the variable y because there's no y squared term, but it is quadratic in the variable x. So finding the x-intercepts is going to involve solving a quadratic equation. Probably a little bit easier than most of the quadratic equations we tangled with in section 1.4. but quadratic nonetheless. X-intercepts. There are a couple of them, or there could be. Let y be 0, and so y equals, so 0 equals x squared minus x minus 6. Can we factor it?
-3.
So x minus 3 times x plus 2. Set each factor equal to 0. X minus 3 equals 0, or x plus 2 equals 0. So we get two solutions to this equation. Points to plot would be 3, 0 and negative 2, 0 if we're plotting points as intercepts. But I think it's going to want 3 comma negative 2. Now, it does not want parentheses. It would never be appropriate to indicate the list of intercepts in parentheses. That makes it look like an ordered pair, or worse yet, interval notation. Makes it look like a point or interval notation. But it's none of that. It's just a list of all x coordinates of x-intercepts. The y-intercept is considerably easier here. Since the equation is solved for y, if we want to find the y-intercept, all we do is let x be 0, which amounts to saying 0 squared minus 0 minus 6, or 0 minus 0 minus 6, or negative 6. So the point 0 comma negative 6 is the point on the y-axis. So negative 6. Are those hard problems or easy problems? Finding x and y intercepts of a straight line, linear equation. Find x and y intercepts of a easy. Good. Let's see. 3. I'm worried about that because I was. No? Okay. I've locked up the screen. Again, without graphing. Okay, determine whether the equation has a graph that's symmetric with respect to the x-axis, y-axis, origin, all of the above. That's not one of the options, I guess, but in general it could be. An equation could have a graph, could have symmetry about all three of these. None of the above is the other option. Procedure for testing an equation for symmetry. And basically just a little bit of the rationale that would have been discussed in the videos. How to do this, why it works. If we have an equation that has x-axis symmetry, I'm thinking this one does not, but if we had one that did, and the point x, y is on the graph, what other points must be on the graph for x-axis symmetry? It's got to be, well, I'm trying to make it this one right here. So for x-axis symmetry, same x, opposite y. So if we're testing for x-axis symmetry, we replace y by negative y and simplify. See if we can make it look like the original equation. Because whenever xy satisfies it, x negative y must also satisfy it. So it would give us an equivalent equation. For y-axis symmetry, which is what we'll do here, if we have something like this, and it has y-axis symmetry, whenever xy is on there, its image, what's its image across the y-axis? Negative xy. Same y, because you're going straight across, but it's on the opposite side of the y-axis. So negative xy is going to be on there when xy is on there. So what we'll do for y-axis symmetry is replace x by negative x and simplify. If we can make If we can make that look like the original equation or something that's equivalent to it, then it'll have y-axis symmetry. Otherwise, it won't. Now, I'm running out of room there. What would we do if we wanted to check for origin symmetry? Got to do both at the same time. If x, y is on there, then go directly across the origin, negative x, negative y also has to be on there. So do both at the same time, x by negative x, y by negative y. Sometimes that works when neither negative x for x and negative y for y, neither one of those work. So that would give us origin symmetry. In this case, we look at it, maybe we suspect that it has y-axis symmetry. So to test for y-axis symmetry, we replace x by negative x, and we check it. Y equals negative x quantity squared plus 12. And I don't know, I made a bigger deal out of it 2 years ago when the videos were recorded than maybe sometimes I do more recently. What's the square of negative x? X squared, yes. Square the negative and you get positive, but square the x and you get x squared. So positive x squared plus 12. So after simplifying, we look at it and we ask ourselves, is this identical to the original? And, except for maybe the size and the shape of the characters, yes. They're both y equals x squared plus 12. They are identical. So they're certainly equivalent, so this means it has y-axis symmetry. Now there's still a possibility, not according to this, because all of the above is not an option, but in general, all of the above is still on the table as soon as you verify it has one of the 3 types of symmetry, and you just want to verify that one of the other types is missing. So if we substituted negative y for y in an attempt to check for x-axis symmetry, negative y equals x squared plus 12, and we're looking at that. Gotta stay away from the left-hand side of the screen, sorry about that. Negative y equals x squared plus 12. Not much simplifying to do, just kind of lose the parentheses. Negative y equals x squared plus 12. Is this identical to the original? Oh, we've got a negative y down here where we had just plain old y in the original. The next question would be to ask, though, is there an algebraically legal maneuver that we can perform on this equation to make it identical to the original? And the 2 key algebraically legal maneuvers that one might typically do are multiplying both sides by negative 1. Sometimes substituting these negatives in there gives us a bunch of negatives, but we can remedy that by multiplying both sides by negative 1. If we do that, we get y equals negative x squared minus 12. It fixes the y, it messes up the other 2 terms. So that doesn't work here. The other typical algebraically legal maneuver that we might do is if we have a fraction on one side or the other, we might multiply both the numerator and denominator by negative 1. That really isn't the case here. So this one really appears only to have y-axis symmetry and neither x-axis symmetry, and if we believe it doesn't have x-axis symmetry, then it can't have origin symmetry either. It cannot have exactly 2 out of 3 of these types of symmetry. So y-axis symmetry only here. And the graph on the calculator certainly will confirm that. If we graph y equals x squared, I've got a good portion of it here. I'll just edit clear. Y equals x squared plus 12, zoom 6. Should get a decent graph in the standard. Oh, no, we don't see that at all. It's above the standard viewing window, sorry. Set the y max maybe to what? 30? And a y scale of 5. Now try y equals x squared plus 12. That's better. y-axis symmetry, so you can see it there. Y equals negative 7x to the 4th plus 2x to the 6th. What's your best guess as to which of the three types of symmetry this may have? The y-axis symmetry? Yeah. The even exponents on the x's are kind of hinting to me that it might have y-axis symmetry. So that would be the first thing I might check. Check y-axis. Well, it's asking for the x-axis symmetry. Let's just note that it doesn't have x-axis symmetry, because when we substitute negative y for y, we get negative y equals negative 7x to the 4th plus 2x to the 6th. Negative y equals negative 7x to the 4th plus 2x to the 6th. This, like the one we looked at previously, is not identical to the original. If we multiply both sides by negative 1, that's not going to be identical to the original either. So let's just say no to x-axis symmetry. Y-axis symmetry, I think there's considerably more hope for. Y equals negative 7 times negative x raised to the 4th plus 2 times negative x raised to the 6th. And what happens when we take negative x and raise it to the 4th power? Well, the negative becomes positive. What does the x become? X to the 4th. It's like 4 negative signs in there that all multiply together. Negative times negative times negative times negative is a positive. And 4 x's in there, x times x times x times x, which give us x to the 4th. So we get positive x to the 4th, and more of the same. 6 negatives all multiplied together. Negative times negative times negative times negative times negative times negative. 6 negatives multiplied together give us a positive. 6 x's all multiplied together. X times x times x times x times x times x is x to the 6th power. So we get positive x to the 6th power there. So not too much in the way of simplifying. Y equals negative 7x to the 4th plus 2x to the 6th. This is identical to the original. So although it did not have x-axis symmetry, it does have y-axis symmetry. So we can say yes to that. And if MyMathLab was okay that we said no to the x-axis symmetry and yes to the y-axis symmetry, then we better say no to the origin symmetry, because it can't have exactly 2 out of 3 of these types of symmetry. So that's a no. You might look at the graph and see this particular one with the higher exponents. Sometimes it can be tricky to find a good viewing window. Negative 7x to the 6th plus, to the 4th, plus 2x to the 6th. I'm going to try that viewing window and see if we can see any portion of this graph. Kind of. What little we see does appear to have y-axis symmetry. A better viewing window might have the x-min, whoops, not that, second quit, window might have the x-min equal to maybe negative 5, the x-max equal to 5, y-min a little lower, and y-max seemed to be okay. There we go, a little bit better viewing window there, but either way we can see it has y-axis symmetry. What are the odd exponents telling us? Oh, it's not going to have a y-axis symmetry. And let's see. Let's check for x-axis symmetry. If we check for x-axis, we'll say negative y equals negative 2x to the 7th plus 3x cubed. This is not identical to the original. Is this identical to the original? Multiplying both sides by negative 1. Not really. So we've got to say no to the x-axis symmetry. So it doesn't have that. Not feeling great about y-axis symmetry either. If we go y-axis, it's going to be y equals negative 2 times negative x to the 7th plus 3 times negative x to the 3rd. So y equals negative 2 times 7 negatives all multiplied together equals what sign of a number? Negative. 7x is all multiplied together. X times x times x times x times x times x times x. X to the 7th. So negative x to the 7th. Like that. That's actually a big deal, being able to grab that 7 and bring it inside the parentheses, because rather than having negative x written 7 times, we have x written 7 times and just one negative sign in front of it. And more of the same here. This is 3 times for the very same reason, because 3 is odd. That 3 can come inside. We still have the negative though. So y equals negative 2 times negative x to the 7th is positive 2x to the 7th. And then positive 3 times negative x cubed would be negative 3x cubed. A lot of simplifying. Is this identical to the original? It cannot, because we have the plus minus sign pattern on the right. We have the minus plus. We can multiply both sides by negative 1, and that would fix the right-hand side. It would mess up the left-hand side. So this is a no. No to that. No to that. Is it symmetric with respect to the origin? That's still a possibility, because the first two failed. For origin symmetry, we substitute negative y for y, but at the same time, we substitute negative x for x. Now what we can do is just kind of go through the same discussion as to how we simplified this. Some room here. How we simplified the right-hand side, because the right-hand side, when we were checking for y-axis symmetry, is pretty much identical to the right-hand side here. So simplify the same sort of way. This is negative y equals negative 2 times the negative of x to the 7th plus 3 times the negative of x cubed. And so negative y equals 2x to the 7th minus 3x cubed. So careful of the first question. Is this identical to the original? Minus plus minus, plus minus plus, not identical to the original, but yes, it can be. There is an algebraically legal maneuver, namely multiplying or dividing both sides by negative 1, that we can perform on this equation to make it identical to the original. So y equals negative 2x to the 7th plus 3x cubed. And now, this is identical to the original, so this has origin symmetry. That's a yes to origin symmetry. So we would say it has origin symmetry only. It has origin symmetry but does not have either of the other two types. And that's all the examples so far of origin symmetry, so that graph is probably worth a look. Can scoot that over. Let's see, maybe if I expand it. Maybe just slide it. Okay, good enough. So y equals negative 2x to the 7th plus 3x to the 3rd power. Perhaps the viewing window I previously had for the other one would work as well for this one. Let's try it and see. Graph. Not so bad. I think I could have gone with a lower y min and a higher, lower y max and a higher y min. Let's go with maybe negative 10 to 10, something closer to the standard viewing window. I can adjust the y scale back to 5, but this is fine. Y min of negative 10, y max of positive 10, and that way the graph, as it goes close to the origin, won't look like it's buried in the x-axis. Graph. A little bit of daylight there between the graph and the x-axis as it goes through. Does it look like origin symmetry? Maybe possibly. Points on the graph, like right there, have their images directly across the origin. If that point's on the graph, its image on the other side is there. If we have a point right there, its image on the other side of the origin is also there. So it has origin symmetry, and we confirm that without sketching the graph. Was that 5? That was 5, yes. Okay, now the instructor created problems. Question 1. Yes, I made this one up myself. I'm the one to blame. Test the equation xy equals 4 plus 8x squared for symmetry as indicated below. So to test it for x-axis symmetry, that's not what it says, but the question, the follow-up question is, this is why we substitute negative y for y. We actually want to substitute negative y for y in the equation and then simplify. So doing the substitution, that much of it probably have room for. Doing the substitution looks like this. X times negative y equals 4 plus 8x squared. It probably doesn't like that though. What we want is, after simplifying, negative xy equals 4 plus 8x squared. That's what I was going for to be typed in the blank there. Negative xy equals 4 plus 8x squared. So I'll put that in there. Negative xy equals 4 plus 8x squared. And I'll go ahead and say no, because not only is it not identical to the original, multiply both sides by negative 1, and that won't make it identical to the original. So we say no and we move on. To test for y-axis symmetry, we substitute negative x for x. Doing so, we get negative x times y equals 4 plus 8 times negative x to the 2nd power. Negative xy on the left, and 4 plus 8 times negative is a positive. X times x is x squared. So basically the same thing we got when we were testing for when we're testing for x-axis symmetry, we get negative xy equals 4 plus 8x squared. So again, that's a no. It's not identical to the original, it's not equivalent to the original. I think it does have origin symmetry though. We test it for origin symmetry. That print is small. When we test it for origin symmetry, we substitute negative x for x and negative y for y, and keep doing that. But what's negative x times negative y? xy. And over here we get 4 plus 8x squared, and that is identical to the original. So since that's identical to the original, that's a yes for origin symmetry. So it's a no there, it's a no there, but it's a yes there, and basically we need to type in a copy of the original equation there. xy equals 4 plus 8x, let me get there, squared, and that's a yes. There we go. So that's what was going on here. So, and it's tough because it really doesn't give me the option of giving you feedback after each part of the question. So you fill in all those blanks, and then it just says wrong. And then it just leaves you wondering, well, which part was it wrong? Is it all wrong, or just a little something here? But hopefully that'll help. Is this a little different? More of the same, but a little different. If we're testing for x-axis symmetry, what clues do we have? The y squared maybe gives us some hope that this could have x-axis symmetry. So let's see. X times negative y squared equals 8 plus 2x. Square negative y, get y squared. Xy squared equals 8 plus 2x, just like that. That's identical to the original, so I'm going to say yes. For the y-axis symmetry, I'm less optimistic. If we substitute negative x for x, it looks like maybe there's some hope because we get negative on the left and a little bit of negative on the right, but not enough negative on the right. Negative xy squared equals 8 minus 2x. I'm going to say no, that's not identical to the original. If we multiply both sides by -1, it would not be equivalent to the original. So negative xy squared equals 8 minus 2x. That's a no. Test it for origin symmetry. I think we're going to get the same result as we did for y-axis symmetry. Is there more room for this one? A little bit.
If it passes X and not Y, or if it passes Y and not X, does that mean it'll never pass origin?
Yes, absolutely. If it has exactly one of those, one but not the other, then it will not have the origin, because having the origin at that point would give it 2 out of 3, and it can't have exactly 2 out of 3. So the rest of it is just kind of...
How come I could have none of those two, but have one?
That it can have exactly one?
No, like.
No x-axis or no y-axis symmetry, yet the origin symmetrical.
We can see the example. You can see kind of what it happens with the x's and y's. If you have, a lot of times what will happen is there'll be an xy term. And when we substitute the negative x for x and the negative y for y, the negative x times the negative y will give us back the original xy term. I mean, just with the x's and y's, that can happen. As far as the graph is concerned, you can kind of visualize maybe something that where you've got up in the first quadrant, the third quadrant.
Yeah, in the picture I see it.
But yeah, it's typically those xy terms multiplied together, and then I don't think any of the MyMathLab problems have all of the above. But if you have nothing but x squared terms and y squared terms, nothing but even exponents on both variables, typically you'll get all of the above: x-axis, y-axis, and origin. But this one, it's gonna fail the origin, right? Negative x negative y squared equals 8 plus 2 times negative x. So negative x times y squared equals 8 minus 2x. Negative xy squared equals 8 minus 2x. Same result as we got when we tested for y-axis symmetry, and this was also a no. So, got to type it. Gotta say no.
Did it matter if you typed it the opposite way?
That's a
where
good.
it's just xy squared equals negative 8 plus 2x?
That's a good question. I honestly don't know. I'm going to find out right now. Because it's been a little while since I put this problem together, and I don't remember exactly how sensitive it is, if everything has to be in the right place, or if it can be algebraically equivalent to that. So it would be good to know. I would like it to accept this, because this is kind of the honest result of trying to perform algebraically legal maneuvers in an effort to see, is this identical to the original? And I think this is a really good faith effort, maybe even better than the other. Might not like it though. Ooh, that hurt. So I would say probably don't do that. Instead, just clear the parentheses. Do that instead. That's a good question. I was thinking that, but I wasn't sure exactly which way it would go with that. I kind of suspected it might not like it though. And I wonder if this link still works. Sometimes on the integrity videos, they'll go to archive, and this is probably at least a couple of years old. Let's see if that'll pop up. Oh my, I was sitting in my office doing that. In a really good mood, apparently. Okay, so if you want to see re-recording it right now, but that would work. Test the equation for symmetry. Kind of have the idea which of the three types of symmetry is 4 minus y equals 3x squared going to have? The y. The x squared term tips us off to the fact that it's going to have y-axis symmetry. If it also had a y squared term, it might also have x-axis symmetry. But I'm thinking this is going to have the y-axis symmetry. So it looks like 4. If I substitute negative y for y, that would be 4 plus y equals 3x squared. If I substitute negative x for x, that would be 4 minus y equals 3x squared. Square the negative x, and it gives us the x squared right back. So if I do both, I would get the 4 plus y as a result of substituting negative y for y, and I would get the 3x squared as a result of substituting negative x for x. The one that gives us the one that's identical to the original is this one. So a yes to the y-axis symmetry, a no to the other two. Okay. Both an x squared term and a y squared term. What's it going to be? All of the above. Substitute negative x for x. It's going to give you the x squared term right back. Substitute negative y for y. It's going to give you the y squared term right back. And they're basically independent of each other. But negative x, negative y. Here I'm technically testing for origin symmetry, but you can see these act independently of each other. So you'll get x squared plus y squared equals 5, whether you do negatives for both of them or just one of them. So this is going to be all of the above. And what would the graph of that look like? It is a circle. It is a circle. We look at equations of circles in this section. X squared plus y squared equals 5 is a circle centered at the origin with the radius length the square root of 5. Funny that they chose the 5. I would think they would have chosen a perfect square, but the radius length is the square root of 5. Finally, they give us a picture. There we go. Got a picture. Draw a complete graph, or choose from the available complete graphs, the one that has y-axis symmetry. There's only one that I see that has y-axis symmetry. Draw a line straight down the middle, up and down, and the two halves of it will be mirror images of each other, the red graph and the blue graph. And I'm thinking it's this one. Is it this one?
Yes.
Yes. So this one will have y-axis symmetry. Points on points on the right, points on the left are images of each other, the same distance from the y-axis, and on opposite sides of the y-axis. There we go. B.
What would a graph look like that had no symmetry?
No symmetry? Maybe just draw something at random.
Yeah.
No symmetry, just something like that. Now there are other types of symmetry that would go. I mean, symmetry about other straight lines other than the x and y axes, and points other than the origin. But let's see, I'm trying to think something meaningful, but yet that didn't have any of these three types of symmetry, or maybe they had a type of symmetry other than these. When we look at quadratic functions, later section 3.1 will be all about quadratic functions. They'll have what's called an axis of symmetry that's not necessarily the y-axis. What will happen is we'll find the vertex. Maybe we'll find one that has a vertex at the point 2, 4, and goes through points like this and points like this, and has a graph that's a parabola. Try to do that, but the screen is too much friction. There we go. A graph like that. Now this doesn't have y-axis symmetry or x-axis symmetry or origin symmetry, but it does have symmetry. The graph is symmetric with respect to this vertical line. X equals 2, yeah. X equals 2 is called the axis of symmetry for this quadratic function, its graph. And it's important for a variety of reasons. The vertex, the highest point or the lowest point, is always going to be on the axis of symmetry. And if you know certain coordinates of certain points on one side, then you get points, their images, for free, just by reflecting across the axis of symmetry.
And in order to have all three, it
Uh-huh.
has to be a circle, right?
Oh, that's another good question. other possibilities, and I tell you what, let's just for examples of these, and I think officially we've covered the sections that are going to be on tomorrow night's quiz. Is that right? So the rest of this is just extra, but I hope it's helpful extra. Other examples, of course, we've got the circle. What if we try to think a circle that somebody sat on, or maybe a circle that somebody kicked? What's this going to be? 4x squared plus 9y squared equals 36. Circle that somebody sat on, or a circle that somebody kicked? Circle that somebody sat on. Does this have all three types of symmetry? Yep. I mean, it's certainly the x and y axis symmetry are pretty straightforward, but if you've got a point right here and you want to know, is its image on the other side of the origin also on the graph? Well, there it is. You just march directly across the origin, the same distance out the other side. So ellipses, also a graph you might not think about. I should close the algebra view. There's, if I change that plus to a minus, this is free math here because we typically only do this in pre-calculus. What about this? Who knows what this is called?
An hourglass.
Kind of looks like an hourglass, huh? It's officially a hyperbola, but it has all three types of symmetry. You can see how you can reflect it about the y-axis, you can reflect about the x-axis, and, like I did before, pick maybe a point right, I can't find a good one, a point right, let me better start over here. Still can't find a good one. I'm looking for something on a grid. I guess I could go right here. If I march directly toward the origin and then out the other side, the image of that is also going to be on the graph. So it also has the origin symmetry. So these conic sections, they're called, not only circles, but ellipses and hyperbolas have this type of symmetry. You can draw a square with its center right on the origin, or a diamond, and get all three types of symmetry. So there's a lot of neat possibilities, in addition to, of course, the circle. Yep. All right. Is that enough? That's enough, I think. Okay. Quiz.